So, good morning. Just so the first poll everywhere question isn't what happened, and so you can actually focus on the rest of the talk. This is what happens when you decide to go for a quick mountain bike ride on Sunday afternoon because you know you're going to be stuck inside for the rest of the week. So I should have been thinking about the trail I was riding and not practicing my talk in my head as I went along. Anyway, as we've just heard, we have a very substantial existing forest resource in the ground. And while we're talking about radiata pine, it's a single species, our planted forests actually are very diverse in terms of the sites that they cover, the genetic stock that's in them, and the silvicultural regimes. And there's been considerable change in our forest management practices over the last sort of 25 to 30 years. And there will be future changes going forward as well. And so if we just look at the sites that our forests are on, they have changed over time. You know, we've seen in the early 1990s, there was a big wave of afforestation on fertile ex-farm sites, and that will have impacts for both growth and wood properties. Our genetic base has changed, and you can see there in the figure on the left that if you just look at the last sort of 12 years or 12 to 13 years from the MPI's nursery survey, just the mix of genetic stock that have been sold has changed. You know, we've seen in the last rotation we're harvesting material that was probably some original open pollinated stock. We went to control pollinated, and now we're seeing a greater prevalence of clonal material. So again, that change in genetic stock, the genetic base has changed. And also our silvicultural regimes. We've seen the shift from heavy investment in pruning, and coupled with that generally heavy thinning, to wide spacing, to concentrate diameter in large pruned logs. We've seen a shift away to higher stand densities, higher stocking levels, as we chase greater volumes. So all those things will have an impact on yield and on wood properties. And so if we know more about the impacts of those decisions on the characteristics of these forests, hopefully we can use this knowledge to extract more value and also to help us to make better decisions about the forests we grow in the future. So we're very fortunate to have a huge resource. So we're very fortunate to have a huge resource of large plot trials, and both Peter and Russell in their introductions have alluded to the benefits of long-term research trials, and particularly we have a legacy of trials where we have different genetic stock, different seed lots grown at different silvicultural regimes across a wide variety of sites across New Zealand, and we can use these trials to look at the interaction among those factors and the effects that has on growth, value and wood properties. And one of the key sets of trials are what's known as the silvicultural breeds trials that were installed across a wide range of sites between 1987 and 1994. And we owe a huge debt of gratitude to gentlemen sitting in the front row, Mike Carson, as well as Sue Carson and other colleagues at what was FRI at the time, who had the foresight to install these large trials that, you know, if you look at the planting date, you can add 28 to 30 years to, you realise that they're coming to rotation age during the course of this research program. So we have really truly benefited from, wise decisions that were made by people who went before us. When we get to this program, we were very fortunate to inherit this legacy of trials. And despite the best efforts of a few land use conversions and a little bit of adverse weather events, we still managed to have 27 of these trials still available to us, and we were able to undertake end-of-rotation assessments of these trials, and that's what we're just going to report on some of the findings briefly. So this probably breaks all the rules of PowerPoint slides. I apologise, it is a very busy table, but I put it in because I know that you're going to get a copy, or you have a copy of the printed proceedings. It is 4 slides to a page, so you might need a magnifying glass or very good glasses to read. But what I just wanted to do was to leave you with a description of the trials that we measured. You can look at the forest names, so those of you who have hosted one of these trials, you can actually see which trials relate to your estate. And also, just while on that, I'd like to take the opportunity to thank you for hosting these trials. It's a whole of rotation investment that you make. You obviously take your land out of production for other things you might want to do on the site, and you tend to have researchers coming and wanting to measure things reasonably regularly. But without your support, these things wouldn't happen. So just really wanted to acknowledge your input there. But really what I wanted to highlight was the range of measurements that we made on these trials. We were also very fortunate to get additional funding from the Forest Grower Levy Trust very early on in the program to support the end of rotation assessments of these trials while we had the opportunity to do so. So with these trials, we made the normal measurements of diameter and height, but we were able to do a lot more as well. So we did, on many of the trials, we were able to do pre-harvest inventory. We were able to measure outer wood density. We can take measurements of standing tree acoustic velocity, which is a proxy for wood stiffness, which is important for structural timber growers or processors. We were also able to test a new Resi tool that I think many of you have seen through the work that Marco Lorsberg and Jeff Downs and others have done, where you can actually rapidly predict wood quality using drilling resistance. We did more intensive X-ray densitometry as a sort of test whether this technology could give us meaningful information. We were able to also do some measurements with a handheld laser scanning tool that I will mention a little bit later on, and Dave Pont will talk about more in more detail in the next session. And we also acquired the very first UAV LiDAR data set. Again, sorry, it's a slightly busy slide, but again, just wanted to paint the overview of these trials and the fact that there is a very diverse range of treatments and a wide range of treatments in these trials. And this concept of a density management diagram helps us to understand what we can get, understand what's happened in terms of the development of the trees in these trials. Again, they're printed in your notes, so I'm not going to do death by PowerPoint by going through them. Those of you who've been to quite a few of these meetings are probably quite familiar with the concept of these density management diagrams to understand how different factors combine to facilitate stand development and ultimately yield. But there are probably many of you, there's a lot of new faces in the room who are less familiar, so I was just going to go through an example from one of the particular trials just to illustrate what we can learn from density management diagrams. So these diagrams essentially show the development of a stand over time, and I'm not sure, probably don't have a pointing thing, and I'm going to risk messing things up if I do that, but you can see there, if you start at the bottom, you can look at the stand density. It shows you the relationship between the number of trees you have in a stand and the size of the trees. So when a stand develops, you start at the bottom end of the graph, and you take a vertical line straight up. So as a stand develops, the trees can get bigger because they're free to grow. Essentially, over time, the stand becomes more crowded. The only way for trees to get bigger is essentially for some trees to die. And so what we see is in the higher stock stands, particularly the stand that was planted at 1,000 stems per hectare and not thinned, that the line starts to curve over to the left. And so if we use that information, we can start to understand what is the maximum number and size of trees that a site can carry. This solid red line defines the maximum stand density line, or the carrying capacity for a site. If we know that, then we can begin to develop silvicultural regimes that take advantage of the site's capacity to grow trees. So we want to fully occupy the site with trees. But in order to fully occupy a site, we need to know what that site can actually carry. So if we use these diagrams to interpret our trials, one of the things we can see is that the range of thinning regimes that were installed, as I said, we can see what the maximum size density line is, and from that we can work out the optimal management zone where we want to try and keep our stand over time through our thinning. One of the things you'll observe, and I'll touch on a little bit later on today, is many cases we did very, very early interventions, and so we were thinning our stands to very low stand densities quite early on. If you sort of want to take the rugby analogy, it's like running a very, very complicated rugby manoeuvre, but doing it 10 metres behind the advantage line. So if we want to really take advantage of what a site can deliver to us, we really want to be pushing ourselves into that management zone with our thinning practices. So with these trials and using all this information from these more fully stocked plots, and just as a little sidebar, I remember early on one of the conversations I had with Mike Carson when he was designing these trials was there was a lot of pressure to put a 50 stems per hectare treatment in the trials and a lot of pressure to take the 1,000 stems per hectare treatment out. And I'm so glad that basically Mike pushed back on that and was listened to, because having those extremely high stocked treatments has actually been very, very useful in understanding what site carrying capacity is. And so that's just a little probably recommendation for those of you who are designing trials in your own company estate, is actually the advantages of having treatments that go slightly beyond what you would do as normal practice. So what was probably considered extreme practice at the time that these trials were put in is probably now normal practice, and what was considered more normal practice is actually considered a little bit at the extreme low end. But anyway, getting back to the story here, we were able to use the data from these more fully stocked treatments, where you can see there you've got 1,000 stems per hectare that essentially were unpruned, unthinned, and some other treatments where you've got they were planted at 1,500 stems per hectare, thinned down to 600, and then another one which was a sort of 667 unpruned, no thin, which was actually probably typical of the millennium regime at the time. So over the course of development of those stands, you can see that you're actually starting to get quite a lot of mortality. You're right up against, and in many cases, you're actually over that, what we think was the maximum size density line. So this is very helpful to us to understand the site carrying capacity. And if we look at all those data and we just plot a histogram of the maximum carrying capacity, we can see for radiata pine, on average, it's about 1,200 25 centimetre diameter trees, or their equivalent. But there are actually many sites where we're actually doing significantly better than that. And so one of the big opportunities to increase productivity is firstly to understand how you can increase carrying capacity and then make sure that you fully utilise the site resource that you've got. So we're still continuing to work with data from these trials to really understand the factors that drive carrying capacity, because if we don't realise that we have a higher carrying capacity, we may actually be implementing silviculture regimes that we're selling ourselves short effectively. So again, the other thing we've been able to learn from these trials is just the range in radiata pine productivity. If we want to understand or we want to increase productivity, it's actually very useful to be able to benchmark the levels of productivity that we already have. And so if we actually just look at the maximum mean annual increment that we get in these trials, we see that we get a number on average that's about 27 cubic metres per hectare per year. And one of the things that's actually interesting is the average productivity is actually directly proportional to 300 index, which is what we commonly use as a measure of site productivity. So that's a good thing. If you have a 300 index, say, of 30, on average your maximum MAI will be 30 cubic metres per hectare per year. But what you'll see is that there are a lot of points above the blue line. So you can actually do considerably better, or conversely, if you understock a site, you can do considerably worse. And there actually are a significant number of plots in these silvicultural breeds trials where the MAI was greater than 40, and even a few where the MAI was greater than 50. And having been caught out once before with reporting very spectacular growth rates, we did go back and double-check the plot areas, and we can confirm that one of the maximum mean annual increment values we got was 52 cubic metres per hectare per year. So that makes radiata pine one of the most productive softwoods in the world. So these high levels of productivity are possible. And the way that you achieve that, essentially, one, is obviously have a very productive site, and secondly is to make sure that it is fully occupied with trees. And we just did some very simple work using machine learning to interrogate all the data from these trials, and it wasn't any great surprise that we showed that 300 index and stand density index, so the inherent site productivity and the degree to which you utilise the site define productivity. But it's not just about how much volume you grow. Ultimately, it's how much value you grow. And we were able to use the data from the pre-harvest inventory to see the relative influence of site, stand density and seedlot genetic rating on total stand value at harvest. And again, these data show quite clearly that stand density is a key determinant of realised value. So if you look at for a selection of the trial sites, the grey dots show you the values, show you the complete data set across all of those 8 sites, and the coloured points show you the data from a particular site. But what you can see there is that there is considerable variation among sites, but generally within a site, there's a very strong relationship between stand density and realised value. And we'll touch on that a little bit later on. So these trials also gave us an opportunity to test new approaches for standing tree assessment pre-harvest. At the moment, our typical way of assessing trees is generally a diameter tape, a hypsometer, and an eyeball. So most of our description of the tree, the features that add value like taper, sweep, and branch size and branch cluster frequency, those are generally assessed by eye. And so with the advent of new technologies, and I don't want to steal too much of Dave Pont's thunder, he's going to talk about this in more detail in the next session, but we've got the opportunity to use new technologies such as terrestrial laser scanning to give us more information. I just wanted to give one result here, which was to look at the branch size. So we developed a metric, or Dave developed a metric. He called it the BS score, but I think he meant branch size. And so he calculated this for every 10 centimetre point up a stem, and if you simply plot the value at that 10 centimetre height for the first sort of 12 metres up the stem, you get the profiles that you see there in those graphs. And the different numbers up the top, 200p, 400p, 500up, that designates the stand density of stocking. So that's 200 stems per hectare, 400, the 500 unpruned, that was plant and leave at 500, no pruning and thinning, and 600p was plant at 1500, thin to 1600 with low prune. And what you're really seeing is the branch size profiles up this tree, and what you're seeing there is what you would expect to see. I think that if you don't do any pruning or thinning, you have relatively wide growing space, you get large branches. If you look to the next panel, you see the 600p. When you plant it at 1500 and you thin down to 600, you're getting quite good control over branch size, given that earlier higher stocking. So these new technologies such as terrestrial laser scanning, as Dave's going to mention, the precision and the range is only going to get better. I think they offer us a lot more promise to capture data like this from long-term trials. The other thing we've also looked at is internal wood properties. And so higher stand densities also have positive impacts on wood density. You can see there's a general positive trend. And again, as we know, wood density differs among sites as well, generally determined by temperature. And we see a similar result for wood stiffness. We measured the wood stiffness, we measured a proxy for wood stiffness, acoustic velocity, just in the outer part of the tree, using a portable acoustic tool, which is shown in the top right. And we can see a strong relationship between stocking and wood density. But just the one caveat on that is that just tells you what's happening on the very outside of the tree. It's really important to understand what's happening throughout the tree's entire cross-section, because that's what affects the wood when it's processed and the outcomes for the processor. As well as those sort of more traditional approaches, we were also able to test other technologies that have come along. I mentioned earlier on the IML resistor graph that you can see in the top right, and that measures the drilling resistance. Marco Lorsberg's done a lot of work around that and can probably give you more detailed explanation if you want to know more. But it's a very rapid means for getting information on wood quality on standing trees, so we were able to test that. We also had a postdoc in the program very early on, Matthew Legg, and he was developing better systems for making non-destructive measurements of stiffness in standing trees using a lot of knowledge he had gained from assessing the pipes in the pipeline industry. So he came up with a system that gave much better correlations to measurements you would make on logs. But as you can see from the figures there, it was very much a prototype, and we'd have quite a bit more development to do to get it to an operational tool. You can just see the simple number of transducers that were attached to the tree. But again, it shows that we can get better information on the internal attributes. we weren't just focused on density and stiffness as well. We were able to go back and look at the comprehensive data set that was collected during the Wood Quality Initiative. And I think you'll hear quite a bit today about the opportunities for sort of big data and machine learning, and to be able to gain new insights from these data sets, where in the past we might have put them in the too hard basket. You know, sometimes our statistics was probably limited to Microsoft Excel. We can do a lot better than that now. And by combining data on the features of interest with tree and climate and soil properties, we can start to tease out some of the signal from the noise. And if we went back, we were able to go back and we looked at resin pockets and intra-ring checks, which are two of the major defects for clearwood producers, and we were able to start to tease out some of the climate and site factors that were associated with them. And we tended to see that low rainfall in the year preceding was often associated with the presence of those features in the year following. And elevation was another factor that came out as being important. So if we have a lot better knowledge about the resource that we've grown, how can we use that knowledge to gain better value at the point of harvest? So in forestry, one of the things we'll know we do is we can spend 28 to 30 years creating value. And it might sound a little bit trite, but it's probably 10 chainsaw cuts and a 100-kilometre trip on a truck. That's actually where we do our value realisation. So can we make better decisions with the information we have at that particular intervention point? So really, when we get to merchandising, this is the key interface between forest growers and wood processors. So processors and customers, they really want logs that are best suited to their process or product at the lowest cost possible. So we talk about the right tree, the right place for the right purpose. They want the right log for the right purpose at the right price. And so there are a lot of opportunities where we can actually intervene and try and better understand and better match the logs that we produce to the requirements of our customers. So we can do that at the standing tree. We can do it potentially at where we do mechanised processing. We can do it either on a landing or in the mill yard. And we potentially can do further in-mill bucking or merchandising at a centralised processing yard. So all this is technically possible, but it comes at a cost. And we'll only do this, essentially, if the benefits of doing so outweigh the costs of implementing it. So this has always been a kind of controversial question in forestry. And so one of the things we did in the program, and when I say we, I really mean Glenn Murphy, who was part of the program for the last 6 years, was to develop this modelling system called SegMod, which was designed to enable us to evaluate different segregation strategies, not just for their impact on wood quality or wood properties of the end product, but actually on the economics of the supply chain. So what it does, it allows us to calculate what we'd called a return to log value, and I'll explain this on the next slide. And then it can optimally buck the stem to maximise those return to log values. And through doing so, we're able to facilitate comparisons of different segregation strategies or merchandising strategies. And so you can just see there a screenshot of the model. It is freely available to levy payers, so if you're interested in doing some runs with it, feel free to come and talk to me or to email Glenn. And it's designed to use standard forest inventory formats. So when I mentioned about it calculates a return to log, I've called it stumpage, and I can only do one inverted comma. But you start with a log specification that's based on internal and external attributes. From using a lot of knowledge from the old FRI and Solid Wood Initiative sawing studies, we're able to determine, firstly, volume conversion, so how much sawn product do you get out of a log with particular characteristics, and then what is the actual grade conversion, so how many for example, number 1 clears do you get if it's a pruned log, or MSG 8 timber if it's a structural saw log. If you know the prices of those products, you can calculate the gross log value. You know something about the cost structure of the sawmill, you can convert that to a mill door value for the mill, and then you work your way around. If you add in the transport and harvesting costs, you get back to a standing tree value, and if you add the inventory costs, you get a pre-harvest inventory equivalent stumpage value. So that was all nice and all well and good, developing it as a sort of a modelling system, but we wanted to see if it gave us sort of sensible results. So we applied it in 4 regional case studies where you had different combinations of forest resource and processing. So we seeded the model with price, cost and stand data from the companies operating in those regions. And again, we thank you for your participation and often giving us data that are reasonably sensitive to you. We were able to model different segregation strategies that involve segregation approach. So where did you segregate? Did you segregate based on pre-harvest inventory data? Did you do pre-harvest inventory data plus standing tree wood quality assessment? Did you do it based on log assessment at a skid site? Did you do it based on a central processing yard, or did you segregate in the mill? We also looked at stand type, whether it was pruned or unpruned. Stand location, was it on flat terrain or on steep terrain, because that will affect your cost structure. We looked at the market focus. So were you looking at a focus on export, or were you focused on the domestic market where the requirements of the customers may be more exacting? And we also looked at location, because clearly there's a transport cost associated with sending material to different processing plants, different distances from your forest. And the number of sorts that we did depended on where and when the segregation was done and the market focus. And pretty much what we found was that if we looked at the scenario that gave us the best return to log for the either at mill door, so that's for the processor, or the stumpage, which is the return to the grower, we can see that for the grower, doing some segregation based on pre-harvest inventory data or at the landing generally gave us the best outcome, certainly compared to no segregation. If you looked at the mill owner, from the mill owner's perspective, doing segregation of the resource based on assessments at the landing gave us the highest returns. And those returns they were typically 5 to 7% higher than the no segregation approach, but they could be as high as 10% better. So that, to us, appeared like a very good opportunity to gain extra value at the time of harvest, simply through better understanding of what you had and making good decisions with that information. So if we move a little bit further back now, if you're sort of partway through the growing cycle, you've got to mid-rotation. We wanted to ask the question of what can you do at mid-rotation to increase the value of your stand for the future.